Hamiltonian Mechanics. Recall generalized momentum. We wrote Lagrange equations in terms of change of generalized momentum given by partial derivative of Lagrangian with respect to generalized coordinate. So our job is to formulate Hamiltonian mechanics, which is formulated in terms of generalized momenta and generalized coordinates. Definition of Hamiltonian we write in terms of sum of all generalized momenta and generalized velocities minus Lagrangian. So this is the Hamiltonian. Now, Hamiltonian is always expressed in terms of generalized positions, generalized momenta, and time, as opposed to Lagrangian, which is expressed in terms of generalized coordinates, generalized velocities, and time. So our job is to substitute variables and get rid of velocities, q dots. To do that, we can write generalized velocities from the definition of generalized momentum and express generalized velocities in terms of generalized coordinates and momenta. In other words, our dynamic variables are generalized coordinates and momenta. So let's rewrite equation of motion in terms of new pair of variables, generalized coordinates and generalized momenta, as opposed to generalized coordinates and generalized velocities. Our definition really says the following, that Hamiltonian, written in terms of all coordinates, all momenta, time, is given by a sum over product of p and velocities q dot sub I minus Lagrangian, which of course is a function of generalized coordinates, generalized velocities, and time. So our job is to change variables from position and velocities to position and momentum. What we're gonna do, we're gonna find a full differential of Hamiltonian first using the left hand side, simply using chain rule. So left hand side gives us full differential of Hamiltonian, and here we have a sum, partial derivative of Hamiltonian with respect to q sub I times full differential of q sub I plus partial derivative of Hamiltonian with respect to momentum p sub I times full differential of momentum sub I, and plus partial derivative of Hamiltonian with respect to time if there's any explicit dependence of Hamiltonian on time, and times full differential. So this is the left hand side. Now let's do the same for the right hand side. So here we'll have a few more terms. So the first term, pi times q sub I dot, is going to give us two terms. It's going to be p sub I full differential dq sub I dot velocity plus q sub I dot full differential of momentum dp sub I minus the Lagrangian is going to give us the next three terms, which are going to be partial derivative of Lagrangian with respect to generalized coordinates q sub I times full differential q sub I minus partial derivative of Lagrangian with respect to velocity q dot sub I times full differential of velocity dq dot sub I. And then we can close the sum, but there is one more term, and this term is minus partial derivative of Lagrangian with respect to time times dt. Okay, so these two obviously are equal. Let's take a closer look at the expression we got from the right-hand side. So we see that partial derivative of Lagrangian with respect to velocity is nothing other than definition of generalized momentum P sub I. Also, partial derivative of Lagrangian with respect to generalized coordinate is nothing other than P dot sub I. We cancel the first term and the last term in the sum. So having right-hand side and left-hand side, we can now compare these two expressions. And we should note that in order for this to be equal, all of the prefactors in front of full differentials must be equal. So in other words, the term in front of dq sub I should be equal to this term here in front of dq sub I, and the term in front of dp sub I should be equal to this here. We get a pair of equations for each variable q and p, and let's write them out. So q sub I dot, therefore, is equal to partial derivative of Hamiltonian with respect to momentum component p sub I, and pi dot equal to minus partial derivative of Hamiltonian with respect to q sub I. So what we have just written is Hamilton's equations of motion. For all I goes from 1 to n, these are Hamilton equations of motion. From the equating of the prefactors in front of time differential, this here, we get the following relationship. Partial derivative of Lagrangian with respect to time is equal to partial derivative of Hamiltonian with respect to time, with a minus sign. So this is our third equation. Why do we formulate Hamilton's mechanics? We'll see in the next lecture that motion looked in terms of momenta and positions can be represented graphically by using Liouville's theorem in the way that you cannot represent the motion by using generalized coordinates and velocities. So we get new insights into the dynamics. Let me point out one more consequence of introducing Hamiltonian, which is rather interesting. So let's reproduce the equation for full differential that we got from the left-hand side of the equation above. So now let's substitute using Hamilton's equations of motion the partial derivatives Hamiltonian. So what we get for the first prefactor, we are getting minus dpi dt, full derivative of momentum. And for the second term, we are getting dqi dt. So you can note this whole sum goes to 0. It gives us another interesting result from Hamiltonian mechanics, that full time derivative of Hamiltonian is equal to partial time derivative of the Hamiltonian. So when we are considering full time derivative, it is equal to partial derivative of Hamiltonian as evaluated on the true trajectory of the motion.